So I want to thank the organizers for the invitation. I really value this symposium where we mix different science. In fact, this is the spirit of what I will talk of. As Michio Yamada was saying, so I had the idea of Mathematics of Planet Earth in 2009. The event took place in 2013. I'm a pure mathematician myself, but I could say my privilege as a researcher is that I'm a student for life, and I'm always eager to learn new things. And in fact, for several years, I would just learn of many aspects of relation where mathematics can say something on planet Earth, and this is what I want to share with you today. So what does it mean, mathematics of planet Earth? Well, we try to divide into 4 themes, and I will say a bit about the 4. So, a complex planet. Well, we want to describe our planet. It has meteorology, climate, oceans. It has an interior. It's a planet. It's a planet that's inhabited by life. So, how does the biodiversity spreads around the planet? What has mathematics to say with it? It is a planet that's structured by civilizations, and you know that now our civilization, it's a global organization. The financial systems are all interlinked. Our civilization use energy, so what is the role in mathematics in structuring the planet? And finally, last but not least, a planet at risk. So we could have climate change, challenge of sustainable development, and also, well, some risk. For instance, in Japan, you will have earthquakes. So what can we say about predicting earthquake, about trying to mitigate tsunamis and things like that? So what have mathematics to do? Epidemics there. So I will go on the 4 theme. Don't be afraid, I will speak more on the first theme than on the others. When we were trying to think of mathematics of planet Earth, what could mathematics say? We would, in fact, be inspired by this painting of French painter Gauguin. And if you look at the painting in the corner, so you will have these 3 sentences. Where do we come from? What are we? Where are we going? Sentences that we have heard yesterday in the speeches, and that are part of things where mathematics can play a role. So the first thing, we want to discover the Earth. And in fact, if you just go outside and try to learn about the Earth with your eyes, it's difficult. You don't understand many things. So what we like to do is we put our mathematical glasses, and with mathematical tools, we can understand things that we don't see with our eyes. So, for instance, we could discover, so the Greeks would discover that the Earth is a sphere and could evaluate its size. So already 3rd century before Christ. Then Newton could evaluate the mass of the Earth. In the 19th century, there was a big historical saga about the age of the Earth. Its interior, so we come closer to nowadays, 20th century. Its movement as a planet, you will be surprised I have put 21st century. So in fact, there are things we know from the past, but there are new developments in the movements of the planet. So evaluating the mass of the Earth, so we use Newton gravitation laws. So we know it says that the attraction we have to the Earth, it's proportional to the mass, our mass and the mass of the Earth, and inversely proportional to the distance to the Earth. So if we know the size of the Earth and we know Newton constant, then we can evaluate the mass of the Earth. Okay, what does it tell us? Well, we can look around us and say, what's the density of the Earth? And we realize that the Earth is much too heavy to be homogeneous, because if we look to the density of soil around us, we'll see that the density is between 2.2 and 2.9 kilogram per decimeter cube. But the mean density of the Earth is 5.52. So what it tells us is that the surface cannot explain for the weight of the Earth. So it tells us that the interior of the Earth is very heavy. So now so a story of a woman mathematician, a Danish woman mathematician. She discovered the inner core of the Earth in 1936. So she had a mathematical background, but she worked at the Danish Geodesic Institute. And then what occurs when you work at all these institutes, you have stations around the world, and when there is a big earthquake, then it sends some seismic waves through the Earth, and then you record these seismic waves at the different stations. You know at which time you have recorded the signal, and then you try, for instance, you use that to find the epicenter of an earthquake. So she could use this data, and what did she? And then, so you have this data at the surface of the Earth, you record something at the surface, and then you want to understand what is in the interior. So that's what mathematicians call solving an inverse problem. You know the effect, and you want to understand the cause. So, first hypothesis, suppose this is the Earth. You have an earthquake here. So if the Earth is uniform, then the signal travels like that. And then depending on what's your angle of the surface, you can say here, okay, the signal arrives exactly, and here it arrives after some delay. So this is the travel time depends on the angle. So this is what we should have if the Earth were uniform. So the Earth, it was known at the time of Inge Lehmann that it has several layers, and when you change layer, then you probably learned in school of the law of refraction. So if you change speed in one layer from the other one, you have the wave will make an angle with this law. So this was the model of the Earth at the time of Inge Lehmann. So you have the mantle here, and then you are having the core. So this is in fact the picture that's taken for her article, her toy model. So here you have a speed of 10 kilometers per second, and here a speed of 8 kilometers per second. And then you see that the waves are on straight line here, but when they enter in the core, they change direction because it's not the same speed, and here. So what's the lesson here? Here you see you have no waves that should be detected here. Oops, sorry. So if I put it in a 3D setting, if my earthquake is here, in this annular region, I should detect no earthquake signal. But Inge Lehmann, she discovered that some signals were registered in the forbidden regions. So that means there was something wrong with the model. So it doesn't work to put this interior and to match with the data you have on the surface. So this is what the problem. And then she tried to modify the interior to understand how it would match with what you see on the surface. So a model explaining is that you have the core here should be divided into two parts, the inner core and the outer core. So, and for the inner core, so in her toy model, the signal is traveling faster, 8.8 kilometers per second. So that means that so this is what I will explain. So when the signal comes here, it would bend in the other direction. And in fact, when the signal arrives with a little angle with the boundary, then instead of penetrating inside the core, it would be reflected, and then you see we can register signal in the forbidden region. So in the law of the refraction, it tells us that the sine of theta 1, V2 divided by V1, should be equal to the sine of theta 2. And we are in the case where we enter a zone where the second region, the speed is faster. So V2 over V1 could be greater than 1. You may have learned at school that the sinus is between 0 and 1. It could occur if you are very bent like that the sign here would be that this product would be greater than 1, and then it cannot be equal. So there is no solution to the refraction. What does it mean? It means that if you come like that, you cannot penetrate if it's faster. If you come very bent, you cannot penetrate, and then you are reflected. So I will have an animation if you see different rays. So the first would penetrate with a change of angle, and when you come with a quite tangentially, then you are reflected. So now this is just an animation. Of course, you see how the different signal would travel. They all travel at the same time, and you see this is the model of the Earth that's now accepted in geophysics. I will move to the planetary motion of the Earth. So you may have learned of Kepler's law. So it says, in the absence of other planets, then the Earth moves on an ellipse with a focus at the sun. In fact, in this movement, you can realize that the planet goes faster when we are closer to the sun. Of course, our ellipse is close to a circle, but that makes a difference in the length of the days depending on the time of the year. But we don't have just the Earth and the sun. We have other planets. So what happens if we take into account the interaction of the planets? So at the end of the 20th century, so Jacques Lascar, he showed in 1981 that the inner planets are chaotic. So the inner planets, it's Mercury, Venus, the Earth, and Mars. Chaotic means what? It means that we cannot predict the position of the planets for a long period of time. We can predict for thousands of years, but we cannot predict for millions of years, because it's a chaotic movement is a very disordered movement, and if you make small errors, then they accumulate and you lose the control on your predictions. So in a chaotic region, a small error in the simulation leads to a very large error in simulating the system over billions of years. So I told you 21st century. In fact, Jacques Lascar, so he refined his result with a very fine simulation of the solar system in 2009. And he studied, if you make an error in the initial condition, the error will grow, so you don't know where it's in the planet. So what do? You study many, many scenarios in parallel. So he would study 2,500 scenarios in parallel. So he had 2,500 computers running in parallel for several months, simulating the solar system. And his simulations show that we cannot exclude a collision between the inner planets, so Mercury, Venus, Earth, and Mars. We cannot exclude that a planet could be expelled out of the solar system. So, is there any hope to say something of the future on the planets? And as I told you, you cannot, if you make a simulation, you don't know if it's what the solar system would look like. But what mathematics tells us is that a solar system that resembles ours could have this future. So when you make this many simulations in parallel, it tells you many possible futures for solar systems that are similar to our solar systems. So in fact, it gives us a range of possible futures, and some are more likely than others. So these are pictures coming from Jacques Lascar. So you see, this is after 1,000 years. So in white, it's the orbit of Mercury, green is Venus, blue is the Earth, and red is Mars. So this is what we have now. And you see here the date, so it's 3,005 million years. So that means don't be afraid, nothing will happen in the next 1,000 or million years. If things catastrophic occur, it's more of the order of billion years. So here, what do we see? We see that the orbit of Mercury is crossing that of Venus. This is another possible future, so 3,030 million years. And here we have the orbit of the Earth that is crossing the orbit of Mars. Another possible future, so the orbit of the Earth here is crossing that of Venus. And then you see that Mars, instead of being centered around the Earth, or around the Sun, has been destabilized. So, can we explain why the movement of planets is chaotic? Well, there are many planets and they interact. So these are the planets around the Sun, and they are influenced, they are attracted by the other planets. And in particular, what is very important in the solar system is the big planet, Jupiter. So a planet is disturbed by the attraction of the other planets, and if they have almost the same period, or for instance, if you have the Sun, Jupiter, and you have almost the same period, well, Jupiter is always pulling in the same direction. So maybe after a long term it makes a difference. So here is a simulation. So I have the Sun. I have put a big planet, Jupiter, but much bigger than the actual Jupiter. I have put 1/10 of the mass of the Sun. And here you have a small planet that is attracted both by the Sun and by the big planet. So you see that its movement is not regular. It's not the ellipse that you are told by Kepler law because of the planet. Of course, the planet is big, so it's more. But you see what I mean by chaotic. Look, you see no rule. It looks very disordered. Okay, so that's what could occur in the solar system. Life could appear on Earth because we have a relatively stable system of seasons. So we know, you probably all learned at school, the reason of the seasons is because the axis of the Earth has an angle. And when we turn around the Sun, this makes the season. And this axis is relatively stable. Well, if we were having a periodic motion, that's normal. But now I told you it's chaotic. So is it normal that the axis would stable? And in fact, the axis of the Earth is stable, but it's not normal if we compare to other planets. The oscillations of the obliquity of the axis of Venus and Mars were in the past very large. The axis of Venus and the axis of Mars can have oscillations of 60 degrees. That of the Earth, 1.5 degrees. So what's the difference? Again, it's Jacques Lascar who gave an explanation. The moon protects us. So he showed in 1993 that without the moon, the Earth's axis would have very large oscillations like the axis of Venus and the Earth. But because of the moon, then this stabilizes the axis of the Earth. The shapes of Earth. So now I will come to a very powerful idea that comes back to Turing in 1952. The loss of equilibrium through diffusion creates pattern. What does it mean? Suppose you have a big land with sand, dry sand, and it's flat. It's equilibrium. Then you start having the wind blowing. Wind blowing, it's diffusion. If it's flat, well, maybe you have one place where a grain of sand is a bit higher. So it will slow the wind, so you will have more sand going around this. So if you have the wind, then you won't stay with the flat surface, and in fact, so you will see this in dunes. So in nature, you will never see a flat area with a flat area with sand. You will always see oscillations. So when we have diffusion, it creates pattern. when we have wind, it creates waves. You won't see the water. And then a model I want to describe when we could have also vegetation patterns. So I will say a bit on this model. So as I say, it's an idea that we find in many, many places in science. The idea was introduced in Turing in 1952 to explain morphogenesis. So we are very far from the shape of the Earth, but the same idea you see in many places. So let's come to a model that would explain sparse vegetation pattern. Well, there is not enough water for a uniform covering with vegetation. And on the other hand, you could have sparse vegetation. Why? There are what we call feedback mechanisms that explain why the vegetation can persist. Because when you have just a little vegetation, well, you have the roots of this vegetation, and they can use the water when there is rain, they can use the water from all the neighboring region. But if there was vegetation all over the place, there wouldn't be enough water for all the vegetation. But there is enough water for some patches of vegetation. And then the second thing is that the vegetation limits the evaporation. So when you have water, and then the sun evaporates the water, but under the patch of vegetation, it stays humid. So that means it helps the vegetation. When you have the vegetation, it keeps the moisture, so it helps the vegetation to stay. This is what we call the feedback, because the phenomena helps to continue keeping the vegetation. So the model, the mathematical model forecasts 4 types of patterns. So you could have gaps, and these are photos. Well, I took them from internet, but that show that the patterns that are predicted by the model do occur in nature. You could have gaps of vegetation. You could have what is called labyrinths of vegetation. You can have spots, so vegetation all over the place except some small spots. And you can have some stripes, and this you see along slopes. So if you have a slope like that, you could have stripes in the perpendicular direction. So we have a model, and it explains what we see in nature. And I told you that the model is universal. So in fact, a similar model could explain the patterns in animal coatings. So you have the 4 patterns predicted by the model, and then you can see the spots in the leopard, the labyrinths in this animal, the gaps here, and the tiger has the stripes. So the same model you see in many places in nature. A lesson from this model is what we call the hysteresis phenomena. So we have this diagram, and then we see that here is where we could have vegetation, so we need some humidity, not zero humidity, and then we will have vegetation, we will have gaps. If we have more humidity, we can have the labyrinths, and more, we can have the spots. Now, suppose you have a very dry summer, and then you go in this region. Then your vegetation disappears, and you come back to no vegetation. But if you have no vegetation, I explain you the feedback mechanism. The feedback mechanism cannot help, because when you have vegetation, it helps keep the moisture, but when you don't have, it cannot help. So when you are in this region, you cannot come back. If the next summer you still have humidity, you cannot come back to the vegetation. You really need to be able to come back to the vegetation to have much more humidity, and then spontaneously the vegetation will reappear. So the very important lesson is that if the vegetation has disappeared, it cannot come back. So this is something which is called a tipping point. No return is possible. So we have seen in a model what is a tipping point, something where you passed and then you cannot come back. And this is something that's important, that when you have nonlinear systems, you can have tipping points. And this is something which is important for the Earth now and when we have the challenges? Are we going to go through tipping points where no return is possible? A biologically diverse planet, so where do we come from? And one big question, so Earth is inhabited by millions of living species, and one important question for the scientists is to explain why we have all this biodiversity. So you have new species that are created through mutations and isolation, and then the species will interact to survive. And how do they interact? So mathematicians like to draw pictures to explain. So this is a picture, for instance, for the interaction between a predator and a prey. So suppose I am here. That means this is my quantity of prey. This is my quantity of predator. So I have little predator, I have prey, so then the prey would grow. But now the predator have a lot to eat. So because they have a lot to eat, then the predator will grow. But now there are so many predators eating the prey that the prey are going down. But now if the prey have gone down, the predator have nothing to eat, so then the predator would go down, and then you see some periodic evolution, and this is observed in nature, that some population have some periodic cycle. So there are other models for computing species. So it's the same geometric picture. Suppose, for instance, this is the quantity of species 1 and the quantity of species 2. And then I follow the line with the arrow. What will happen? Oh, I will end in this place, and in this place species 2 is 0. So I have extension of species 2. If I start here, I end here, 0 of species 1. So if I have strong competition, then it leads to the extension of one species. So that means competition goes against biodiversity. But we have biodiversity. So where does it come from? So we have to find other forces. So one of them is spatial heterogeneity. So for instance, you could imagine that in some region you are here and then species 1 will win, and in other region of the world you are here and then species 2 will win. Another is temporal heterogeneity. I won't take time for this because it just says, well, depending on the season, sometimes maybe species 1 is winning when it's dry, and then species 2 is winning when it's raining, so maybe there is some equilibrium. But the important force that I want to describe is cooperation. So this is illustrated by what is called a prisoner's dilemma, so it's a philosophical dilemma. You are individual 2, I'm individual 1. We both have the choice of cooperating, so you are in red, defecting. And in each place, you see what you get depending. So I have to choose if I cooperate or if I defect. Suppose you cooperate, so you remain silent. If I cooperate, I get 2 years in jail. If I defect, I get 1 year in jail. So my choice is clear. I defect. Suppose you defect. If I cooperate, I get 4 years in jail. If I defect, I get 3 years in jail. So my choice is clear. I will defect. Okay? So whatever you do, I'm better to defect. Why is it a dilemma? Well, you are clever people. So you will make the same reasoning as I did. So you will have chosen to defect. So then you choose to defect, I choose to defect. We both get 3 years in jail. Maybe we should have chosen to cooperate. Okay? Because if you think that the opposite people is making, then we should choose to cooperate. So in fact, cooperation has modeled the world as we know it. So in many species, we could observe mechanisms of cooperation, and they explain the preservation of biodiversity. And it is everywhere present in the organization of the planet. At many levels, the countries, they have the choice of competing and cooperating. But when you see that if you try to have a strategy, the other country will also have a strategy, maybe we are better to cooperate. So I will now say something about the planetary challenge, and then, second question from the picture, so where are we going? The problems are very complex since all systems are intertwined. So already in the Stern Review on the Economics of Climate Change in 2006 would say the benefits of strong early action on climate change far outweigh the costs for not acting. But how to convince government to act? If we act, we have to pay now, but the benefits, we won't feel them now. If you just start putting greenhouse gas in the atmosphere, the real benefits will be in 50 years or 200 years. Do you want to pay now for something in 200 years? That's a difficult decision. The problems will be irregularly felt around the world. Some countries may benefit from global warming. For instance, my country, which is a cold country, maybe new areas will be open to agriculture. Some other countries will be destroyed or ruined. It's not necessarily the same countries that contribute to the increase of greenhouse gas and that will have the most, that will suffer the most from the consequences. So you see that the prisoner's dilemma, we see it everywhere in the decisions. We have the dilemma of depolluting. So you have a cost for polluting, and the cost for polluting, well, each country has to pay a cost when the other countries pollute. And the cost of depolluting, well, you pay alone when you decide to depollute. And then each country, from its own point of view, has no interest in depolluting. But if we all take the decision of polluting, then as a whole, we lose. So it's the same dilemma. The real consequences are unknown. We could expect some ecosystems to disappear. But how will the transition take place? Will it be smoothly? Suddenly you have new plants and animals that are installing? Or will it be very abrupt? You could imagine some ecosystems that are completely destroyed, and then you have an intermediate period before new forests would develop. Mathematicians want to know what will happen, so they try to make models. A challenge for a model is that it only contains what you put in it. So you have some equation, mathematics can say what the equations say, but have you put the right thing in the equation? This is one challenge. So for instance, with Arctic warming, then we realize that now we must take into account the albedo effect. Albedo effect, what it means. If you have the ice in the Arctic, then the sun is reflected on the ice, and then the heat goes up. But if the ice has disappeared, then the heat is absorbed by the sea. So then the sea gets warmer, and then when it gets warmer, then in the fall you have less ice that's forming, and then the next summer you will have more heat that absorb. I have described you one feedback phenomena. This is another feedback phenomena. So this is something that is sort of, even if you stop warming, well, you will have more sea that will absorb more warm, and then it will continue the phenomena. We realize that methane, so it's a strong greenhouse gas, is released by the ocean. So we have to put this in the model. And for the scientists, so this is why mathematics has to work with the other science, the big question is, have we put everything in the model so that we be able to make some forecast? So as I told you, the albedo effect, this is a feedback mechanism. So a big question for the scientists that's not solved. Have we passed the tipping point? So suppose we stop having the temperature rising. Will the ice stay in the Arctic, or will the ice completely disappear just because of the feedback mechanism? The challenge of climate modeling. So climate is a complex system. So when you make some model, you need to make simplification, because if you start having the temperature at each point of the Earth every day, then you have so many data that you don't see the trend. So if you want to see the trend, you need to make simplification. Otherwise, you cannot say anything. At the same time, you must be sure that you put the essential ingredients, because if you have forgotten something that's essential, then you have a model, but it's not connected to the reality. So this is a big challenge for the scientist. So all elements are coupled. So you have the atmosphere, water, ice, life, soil, and then you have some equilibrium between the heat that the Earth receives and the heat that it radiates. So some equilibrium. I won't go into the details. I have been, because of Mathematics of Planet Earth, organizing some schools around the world, and one on climate. And I would go myself to the school to learn more. And I learned, in fact, that something that's a real challenge for the scientists is the clouds. Can we predict the clouds of tomorrow? So the clouds, when we have low altitude clouds, like big clouds like that, then they reflect the heat and then they cool the planet. But you may, if you have these very high altitude, very thin clouds, you may have realized when you see that in the sky, how hot it is. It's like a greenhouse. So the cirrus clouds, they heat the planet. So a big challenge for the scientists is what will be the clouds of tomorrow, because this is an important unknown to know if we will have, how big will be the warming of the planet. So other unknowns that people try to understand, the feedback mechanism. So I have given you an example. What is a feedback mechanism? And the tipping points. That's a big challenge for the scientists. Where are the tipping points? Where are the places where you just cannot decide, okay, we come back, we just stop, for instance, putting greenhouse gas, but then you try and it doesn't stop and you cannot come back. So when are the points where you just cannot come back? To finish, so just an example, moving to an economy of sustainability. This is something we need to do. So we need a scientific definition. What is sustainable development? It is development that meets the needs of the present without compromising the needs of the future. So it's a commission of the United Nations. Is this definition sufficiently precise to guide our actions? So I will give an example with fisheries. So if you have no regulation, you will fish until there is no more fish in the sea. So we should control the access. So how do we control? And one thing that could seem obvious, well, you want to say we don't want just to make money now. We want to make money every year. So the quantity we're allowed to fish is we want to maximize the revenue over years. So it looks like an obvious answer. But of course, the money you make, it depends on the discount factor. I won't go into the details, but for instance, suppose you make money now, you put it in the bank, then you have interest rate on it. So how much money, 1 yen in 10 years from now is not the same value as now. So you want to compare. And the surprising result from Colin Clark in 1973, if the discount factor is at least twice as the reproduction rate, so suppose if you have high interest rate, then you may maximize the revenue by fishing the whole population now and putting the money in the bank. So that means the reason I choose this example is the definition of sustainable development would look obvious, the answer would look obvious, but it's not so easy for scientists to give precise definition and to know what are the real strategies. You see that there are difficulties. So we're having more questions than answers. We discover new pressing problems faster than the known ones are solved, and mathematics has an essential role to play in these issues. So thank you very much.